force and velocity in magnetic field, what happens if everything is perpendicular? So we know that magnetic force, so we'll start with what happens if the velocity and the magnetic field are perpendicular. We know magnetic force FB is charge times the velocity crossed with the magnetic field, QV cross B. So there's two outcomes of this. The first outcome is that our resultant force FB is perpendicular to the velocity V. Right off the bat, that might trigger something that you would think about. If you're not quite sure what I'm getting at, let's just trace that motion through a bit. So here's a positive charge. It's moving upwards in an area where the magnetic field is into the page. And we know it's into the page because it has the little X's. So that means that the magnetic force, see if I can get something a little bit brighter here. The magnetic force is V cross B is to the left. So V cross B, our magnetic force points this way. So our force points in this way. There's our magnetic force. Well, what does that force do? It'll continue to move up because that component of velocity will be constant, but it will also move a little to the left. So a little bit of time later, it's going to be up here. Once it's here, the velocity is a tangent to the circle. The magnetic field is perpendicular to that, so your thumb is with V, your finger is with B, and then your next finger is with F. So now the force is pointing inwards. So then it's going to carry on, drifting this way, but pulled this way, which means it's going to move this way a bit more till it gets up to about here. Velocity still tangent to the circle. Force still perpendicular. Now you probably recognize this a little bit better. Whenever the force and velocity are perpendicular, we get circular motion. And this is the same as all the circular motion examples you've ever seen before. The example that springs to mind is that the moon goes around the Earth, the force is towards the Earth, the velocity is perpendicular to that, so we get a circular motion around the Earth. Now, something about charges moving in magnetic fields is that the force is perpendicular to the velocity, but the force is also perpendicular to the magnetic field. When we have this case, we have circular motion, but we call it cyclotron motion. And there's lots of interesting cyclotrons you can read about. One right here in Canada is Triumph in BC. That's pretty interesting. So you might want to take a quick Google about what Triumph does. This picture right here I nabbed out of your textbook. This is a beam of electrons shot into this little glass bulb that's full of gas. It's also inside of a magnetic field, so we get the motion perpendicular to the field, so you get a force perpendicular to both. And this lit up path here is actually the motion of the electrons. It's kind of neat, you can see it, because the electrons collide with the gas inside the chamber. When it collides with the gas, it excites it, and the gas emits energy in the way of light, so that's kind of interesting. What else can we talk about? How do we analyze this motion? We can do that with our old school analysis. We'll think about Newton's second law. So if we're analyzing this motion, we'll start with the fact that the net force, the sum of the forces on our charged particle, is mass times acceleration. The net force is the magnetic force. Usually forces due to gravity are so small we just neglect them. Our magnetic force, since everything is perpendicular, the magnitude is QVB times the sine of 90, because the angle between these two guys are 90 degrees. And when things go in a circle, we write down our expression for centripetal acceleration, v squared over r. We can solve this for the radius of the path, and we get m times v over q times b. This is the radius of the path of a charged particle in a magnetic field. And this sort of idea is used loads and loads in experimental physics. If you put something in a path like this where you can measure the radius, you can find the charge to mass ratio. That's how we learn a lot of things about new isotopes. Another interesting thing we can think about is, what if our charged particle doesn't just move in this plane parallel to the paper? What if it has another component of the motion that moves out this way? So let's try and think about what happens there. The component of the motion that points out this way, it has no force, so that velocity would be constant. So it would move around in a circle like this, but it would also get a motion like this coming up out of the page. I'll try it with a ball. I'm going to move the camera, so I hope it's not going to make you sick. I'll try it with a ball just to see if we can get a better look at it. And I'm even going to tilt the camera. Hopefully this is not going to be too weird. Okay, so here's the ball on the string. It moves around in a plane this way, but what if it had a component of velocity that was towards the ceiling? Well, it would still move up while it went in a circle. You'd get a helical motion. So that's kind of interesting. You can get helical motion if you add a component of drift velocity. I'm going to publish a written assignment applying that kind of helical motion to the northern lights and see what you can make of that.